Stop. Okay. My thing was freaking out. All right, 23. Calm down, Kevin. So with 23, you have a really simple machine, basically, a pulley. This is the diagram it gives you. You've got a box on a table. It's connected to a rope, pulley, rope, another box that's suspended in the air. It says this one's 70 newtons, right? And then it says determine the force that the table exerts on the box if the weight hanging on the other side of the pulley weighs 30, 60, 90. So A is 30 newtons, E is 60, C is 90. All right, in order to answer this should be pretty intuitive, but in order to really answer this question, you have to draw free body diagrams for both blocks, which is just a good thing to do regardless. So for, let's say this is block A, this is block B. For A, right, we're going to have FG pulling down on the box, which is going to equal 70 newtons. Right. We're going to have some normal force, and what else?
Gravity.
Tension force.
Oh my god.
We're gonna have gravity. Okay. Gravity and tension force. Now we ask ourselves, in terms of the state of this box, is it accelerating? No, it's at rest on the ground. So our net force has to equal what? Okay, 0 newtons. What that means is this plus this has to equal that, right? So you could say normal force plus tension force has to equal 70 newtons, right? So now we're going to look at block B. Yeah. Okay, so block B in the first part is 90 newtons. Oh, sorry, 30 newtons. Getting ahead of myself. What other forces act on block B? Just tension. That's it. Okay, so what sort of block B is, hold on. Block B, what net force are we looking at on block B? 0. It's also at rest, right? So we can say since the net force is 0, we can say 30 newtons has to equal your tension force. Right? And then substituting back over here, you can obviously see that what? The normal force is going to equal what? 40 newtons, right? Hopefully I don't have to go through algebra. Yeah, this is a really intuitive question that you could probably answer without free body diagrams, but since we haven't worked with tension a lot, I wanted to show you one that was really basic. So for 60, it's going to decrease to what? 10 newtons, right? For 90, what's going to happen? Okay, so it's not a negative normal force though. What is it? 0. Normal force would be 0 here. Yeah, you can't have a negative normal force. So yeah, exactly. It's now not on the table. Block B is on the table, so block B would have a normal force of 20 newtons. This is a perfect pulley with no friction. So if this is heavier than this, it will come to rest on the table. If there is friction, then it might not, depending on the coefficient of static friction. If they were equal, then you'd have static equilibrium. So I could move them theoretically wherever, and they would stay perfectly motionless. I could have one on the ground, one in the air, 0 normal force though. If they were equal, there would be no normal force. I could move this one up a little bit, and then this one would move down a little bit, but it would stay perfectly motionless after I let go of them. Of course, that doesn't happen in real life with friction. So that's 23. That's a good one to start off with. Let me see what else. Since we're already on the topic of tension, let's look at 36. 36 is a tougher one with tension. Make sure I'm not leading you awry. 36 is on page 107. If you don't have a book, I have the photos on my website. Okay, so looking at 36, this is obviously a force problem. So our first step is really going to be to draw a free body diagram, but let me get a drawing of the situation first. This is 2.2 kilograms. This is 3.2. The pulley is 4.8 meters off the ground, and the blocks are initially suspended 1.80 meters from the ground. Am I missing anything else? What maximum height does the lighter object reach after the system is released? So this is the lighter object. We're going to try to figure out how high it's going to go. Right? It's going to reach equilibrium before then.
Which object? The light one.
Yeah. Sorry, I keep forgetting. This one's going to move upwards. Right. Okay, so we want to figure out what maximum height does it reach after the system is released. Okay, so doing this, we're going to look at a free body diagram for both blocks. Just like we did before. We'll say this is A and this is B. So for block A, we've got a gravitational force equal to 2.2 times 9.8, which is, I'm just going to round, 22. This should get us close enough to the right answer. And then we're going to have some tension force. That's it for that one. For block B, you have some gravitational force, which is going to be equal close to 32 newtons. Sorry, forgot newtons over there. And then the same tension force. All right, these blocks are not in equilibrium. That's the first thing you have to realize, is that the net force on these blocks is not zero. They're not motionless. And when you set up this system, the very first thing they're going to do is move. Right? So our goal is to figure out some sort of equation we can write so we can figure out what. Well, we're dealing with motion, the acceleration. Okay. No, they don't give time.
Wait, so would it just go up 3.6 meters maximum?
You'll see.
Because one goes down to the ground and it's stopped. The other goes up,
I don't think that's the answer.
gets stopped. You're done.
Yeah, in your brain. Yeah.
Wait, can you say the question one more time? Because
The-
it's asking what the max height is going to be.
Yeah.
Then all we have to do is wait till the thing hits the ground, and then the other one goes up.
The answer, dude, right?
We're done.
What?
Yeah, but that's not it.
That's not it.
I know it seems like it would be. All right. So what we can do is we still can set up a net force equation. It's just we know that the net force is not zero now. All right. So the best thing to do here is, all right, we're going to look at this. We can set up a net force here. Let me make sure I'm writing this down correctly. It's going to be, for this block, it's going to be the force of tension minus Fg. Okay, tension force, whoops. All right, and I'm actually going to do this minus, whoops. Minus MAG. What do we set this equal to? Is equal to M A. Yeah. A. The mass of block A times the acceleration. And then we can do the same over here, except our signs are going to flip. Over here, so when we're dealing with tension, you have to keep the directions consistent. Yeah. So if you're saying tension force here is positive, then this one's negative, right? This is going to be positive. So here we're going to do MBG minus force tension is equal to MBA.
But why is it?
Yeah, M sub A times A. Sorry, yeah, but what I'm trying to show you, I think this simplifies.
What is MAG? What's MAG?
Mass of block A times negative 9.8 meters per second squared. So The other thing that we need to realize is with tension, since our strings are not slack, they don't stretch, right? There's no friction in them. This acceleration and this acceleration have to be equal, right? And that's where we're going to get our equation from. This A equals that A, right? So what we're going to do is, just by looking at the two equations, I think you substitute in. So if you solve one of these for A, and then you plug into the other one, I think something cancels out. Hold on. Yeah, the tension forces have to be the same as well. I think that would be another way to work this out, yeah. That's the best way to do it. I forget what it's called as well. Yeah. So how would we set this up so we did that? Yeah. So let's rewrite that. So Ft minus MAG is equal to MAA. So this one's going to be negative Ft plus MBG is equal to MBA. So when we add these two equations, these cancel out. Okay, so we get, I'm going to write it like this, MBG minus MAG is equal to, I'm going to go ahead and factor over here, MA plus MB, since the A is the same. Yeah. Dividing by MA, well, hold on, yeah. I think G should cancel though. Yeah, that's what it is. It's easier to work with. So that's the equation we get. I'm pretty sure that's the same one that the solution's got. Hold on. A is equal to, what did they say? MB minus MA, yeah. Divided by MA, yeah, okay. So here what you can do is just substitute in and solve. So you're going to get A is equal to -9.8. Mass of block B, that was the heavier one, 3.2 minus 2.2 divided by 2.2 plus 3.2.
That turns to 9.8 if you factor out -1. Wait, no.
So you'll get for your acceleration, it is going to be negative, but if you look at the way we set up the convention, that makes sense. It's going to be pointing downwards on the right side, right? Because that's the heavier side. So saving time, this is what you should get, 10.81 meters per second squared. That's for both blocks. That's the acceleration. Okay. So here, this becomes, from this point, a kinematics problem. Sorry? Sorry? Well, it's not a hugely important. We know it's downwards in our convention. I think the book set it up the other way, where up was negative. Right. So from here, what this becomes is a kinematics problem. We have an acceleration of the block, and we're going to figure out the maximum height of block A. Okay. We don't have time, so the first thing I would try doing is the delta. Wait, hold on. Actually, I think there's a oh no, hold on. I see what the difference is. So to answer your question, Mac, the reason that it just doesn't reach that height is because we go back to the picture. I didn't really know how to explain this, but now I do. We go back to this picture. What's going to happen is the block, while this one is moving, right? The block has an acceleration independent of gravity.
I was asking, like, after it hits that spot, it'll jump up a little bit.
No, it'll fall back down.
How?
So while this one's falling, it's got a force pulling it upwards, so its acceleration is not negative 9.8 meters per second squared. So it's going to go up initially, and it's going to go past what its maximum height is, and then like the string is going to relax, right? It'll pop up, and then it'll fall back down to where it should be in equilibrium, right? So what it's asking is how far up is it going to pop, in other words, right?
Wait, what do you mean by fall out?
If I could demonstrate it for you. Yeah, so basically it's pulling so hard, this block is going to pull harder than the force of gravity. So what you end up having is it's under a constant force from this block until that block hits the ground, right? Once the block hits the ground, then it is accelerating in the negative direction. But all the way up until that point, it's in the positive direction. So it has this positive velocity that keeps it moving upwards before it gets pulled back down. So you'll see the line go slack. It goes up past where you'd expect it to go, and then it falls back. That's why the maximum height is not where you think it is.
So
It's a little bit higher.
We're assuming the string is long enough.
What I'm about to show you.
It's long enough to go.
Well, it would just move straight up. It's not going to flip over. Yeah. Okay, so this becomes a kinematics problem. What you're going to do is
What's the kinetic?
you're going to find the velocity of block 1, the VF of block 1, when this hits the ground. Okay. Really, I'm not too concerned with the last part of this question, so I'm just going to talk through it. The main part that you need to know how to do is solve for the acceleration of both blocks, because that's a forces problem. So I'm not going to work through the rest of this, but what you would do is you have a delta y. Wait, I went too far back. You have a delta y here of 1.8 meters. So you would use that in the time-independent equation, and you'd use the velocity we saw, or the acceleration you solve for, and you'd find out the final velocity of the block after that one hits the ground. That becomes your new initial velocity, because at that point, it's just going to be a projectile, essentially, with no, it's going to be a free fall, in other words. All right, so that becomes your new velocity. Then you use negative 9.8 meters per second squared, and you can solve for the real height. The real height is 3.93 meters. Right, so its maximum height is just slightly above what you would expect, right, of 3. So it would pop about 0.93 meters higher than you would expect. You don't need to know how to do that part. Although this might be a problem, this type of problem might be one that I would give you guys when we're reviewing for the AP test. Because this could be on the AP test. There's not going to be one that this challenging on your test.
Yeah.
But like I said,
This is so hard.
you need to know how we set up these equations here and how we solve for the acceleration of both blocks, because that would be important.
Wait.
Alright, so let's just sum everything up.
Yeah.
Now, the chapter 3 one, we always figure out T and then do all that. So
Not always, but almost
yeah,
all
like
the time.
many times.
Yeah.
So in fourth problem, many times we're gonna use the net force and then use that as
Yeah, you'd figure out first, is net force 0? Because if it is, it's usually a pretty easy problem to work with.
okay.
The net force is 0 when your velocity is constant or you have no acceleration, right? If it's not, then your next step would be to find acceleration. From there,
MA equals whatever.
yeah. So like from here, now that we know the acceleration of both blocks, we could go back and calculate the tension force, for example, right?
But how do you solve for height?
You don't need to know how to do that. It's hard for me to explain without you seeing it. Like if I had a thing, I could demonstrate it for you. Basically, it has an acceleration from the block until that block hits the ground. So you'd find the final velocity when the block hits the ground. Now it's just a projectile, and you'd use that as an initial velocity and do
Oh,
negative
it's like
9.8
an
meters per
actual
second to
height.
see how high it reaches before it starts falling back down again. That's a good problem. Yeah. All right, let's see what else. 81 was another one I gave you. It shouldn't be. Oh yeah, this one goes with static friction and stuff.
Static friction or static friction?
Yeah, let's do 81. So I didn't talk to you guys about static and kinetic frictions.
You're on the test?
No,
Wait.
we just refer to it as friction.
You
But
static like the initial like starting force.
yeah,
Mr. Flores put some problems that I just don't know what we're doing. That
Yeah.
he said that we wouldn't get into the test. I don't know what
I mean, you need to know.
Everything.
Yeah, I can't tell you that those are the only ones because then a student will come in and say, "Hey, I did all the problems. I didn't do all on the test." Well, okay, I can't give you all the problems. I would say if you really know those problems, I also had like I said, I had questions from the other assignments we did. Like if you really know how those work, you should be okay.
Is reading the textbook helpful?
It could be.
It's way more important.
Yeah. So since we're like, have you taken physics before?
Yeah, I think
Okay. Well, we
I think I would do this stuff last year. I forgot everything.
yeah.
Like,
Well, that happens.
remember, like, the
It's a thing called
basics.
summer.
Yeah, I remember the basics, but what I don't remember is the specifics. Like, is it like what to add to become force integral with the
Yeah.
like the details. Like he's like free fall is always.
If you're stuck on those, what I would do is you don't need to read the chapter. I would look at the example problems they work out for you, because usually they'll try to touch on those areas. And then I put all the solutions to the book questions on my website, so you can also look at those. I'm realizing that some of them are a lot harder than I thought. So if you're getting them, that's good. All right. So 81. 81 looks like this. You got some sort of. I'm not going to draw a bucket. Don't need to. Pulley. Block 28 kilograms. All right, so it says a 28 kilogram block is connected to an empty 1 kilogram bucket. So this is 1 kilogram by itself. By a cord, frictionless pulley, blah, blah, blah. The coefficient of static friction between the table and the block is 0.450. So there's static and kinetic friction. We haven't talked about the difference between the two because we haven't really had to deal with it yet. Static friction happens when an object is motionless. So right now we're talking about the object is staying still. This friction is going to apply until it starts moving. So basically what you have to do is you have to have a force overcome this static friction, then it will move, then you have kinetic friction. You don't really need to know the difference though for your test though. And the coefficient of kinetic friction with a table and block is,
It's a lot smaller.
yeah. So once you get it moving, and this should make sense with what you've experienced so far in your life. Once you get it moving, it's slightly easier to keep it moving because your coefficient of kinetic friction is going to be a little bit smaller.
Is that
0.320. So the pen dragged for some reason. Alright, sand is gradually added to the bucket until the system just begins to move. Right, so it says calculate the mass of the sand added to the bucket. So if it's just beginning to move, this is the friction we're dealing with. Right, so essentially what we're being asked to solve for is how much mass are we going to add over here in order to overcome this kinetic friction or static friction. So looking at free body diagrams, does this one matter? I mean, it does, but it's simple. For this one, we're going to have force of gravity, which is equal to mg, right? If you want to, this would probably be a good time to do this. It's going to be m minus 1g for the real answer, because this already weighs 1 kilogram. So if we're looking at the mass of sand, it'd be the mass minus 1. Okay. And here you'd have the tension force.
They're the same.
They are the same here because it's not accelerating, right? Okay, not yet. Over here for this block, the normal and gravitational forces cancel out. So let's go ahead and add them in though, because we're dealing with friction. So Fg is going to equal to 28 times 9.8. Our normal force is also going to be the same, 28 times 9.8. It's on a flat surface.
Isn't there also like a sideways?
Okay, so the force we're trying to overcome is right here, the frictional force. And if we remember, frictional forces are equal to normal force In this case, it is mg mu. But remember, the normal force and the gravitational force are not always the same. Right? Okay, so looking here, if we just want to overcome the frictional force, then we would say the tension force, which I forgot to draw in, the tension force must equal the friction force. And we'd solve from there. Okay,
Oh,
so
we know the tension force, right?
yeah, we know, well, we're going to, right? Okay, so for the frictional force, we have normal mu, right? This is going to equal mgu. Our mass of the block is 28 times 9.8 times the coefficient of static friction is 0.450. Right, so this is going to give us our friction force, which actually we'll probably already have this solved for me. What is this, 81?
So we don't really know the difference?
This? You don't need to know the difference between static and kinetic.
But is it a problem with this one?
Yeah,
Can you on it?
you'll need, there's definitely problems dealing with friction, for sure. Okay. Yeah, they're solving for it a little bit differently.
So is friction always equal to F net times mu? Or does it equal N?
It's always, no, not net force, normal force mu.
I mean, no,
Yeah, it's always normal force mu. Sometimes it's FG mu, but if you're on an incline, then you have to do cosine theta, FG cosine theta mu. Yeah. Okay. So going here, yeah, this is right. They didn't solve it for me then. You saw in the solutions, they do a lot of substituting and stuff. They like avoiding putting numbers into the calculator until like the very last second. 28 times 9.8 times 0.450. So this is our frictional force, 123.48 newtons. So our tension force on the other side has to equal that. Right? And we know from the way we set it up earlier, the mass minus 1 times g is going to be the mass of sand we need to add to equal this. Right? G is 9.8. So the solving for m, you're going to do that divided by 9.8 minus 1. Because it says the bucket is already 1 kilogram without sand. So it's asking how much sand you have to add. So you're going to get 11.6 kilograms.
What if it was like 4?
Well, then it would be n minus 4.
Wait, but I don't understand how that's the same as that, because I know that it's
What
like-
that is that? What do you?
Well, I know tension force is equal to that.
Yeah.
1, 2, 3, but that's not the tension force. Tension
Okay.
force is just times 1.
This is to get the block moving, right? Okay. So the only force that's going to pull this block off the table is the tension force. So what we're going to do is add mass to this right here.
Is it equilibrium right now?
Right now it is, but when we add mass to it, we're going to put it out of equilibrium.
Oh,
That's
so
why
it's
we're
not
saying
right now.
this is basically what we saw for the friction force. This is the max force that the table is going to pull back on the block with. So if you overcome it, now it's going to move. It's out of equilibrium. That's how we were able to say this equals this. Right? Anything just over this is going to make the block move. Right? Okay, so the mass is 11.6 kilograms. Part 2 is not as important. I mostly just wanted to do part A. It says B, calculate the acceleration of the system. Here's where you would have to know the difference between static and kinetic friction. Now that it's moving, you would use mu k, the kinetic friction, which is 0.320, sorry. Okay, so now we've got a system where we've got, on this block, we know Fg is now equal to 120, I forgot what it was, 123.48 newtons. All right, that is just enough, 123.48. That is just enough to get our blocks moving, right? Okay, so that's the force that this thing is going to feel. Right? Okay, 123.48. So what we would do here is calculate the new frictional force using this coefficient. So now it would be is equal to 28 times 9.8 times 0.320. You get an answer here, subtract it from 123.48, and say the mass here, block A, plus the mass of block B, times their acceleration that they share has to equal the 123.48 minus the force of friction. Which, like I said, it's not as important that you know how to do this, but that's how you solve for it.
Where are you getting MA plus
Well, because these are attached by a string.
MB?
The acceleration's coming from this block, but it's pulling this one with it. So you look at it as like one block. Yeah, you combine the system, and then you could solve for A. Right. Yeah. Net force always, well, not always, but you usually want to look at it as a system, not separated. So that was 81. Let's see, 39, 38. So 39, I'm not going to work out. 39 is very similar to this problem. Basically, you're getting a force. It's telling you the force it requires to get the block moving, right? So you could find the static friction just by doing this backwards, basically. If 40 newtons is the force that gets it moving, then the frictional force is 40 newtons. If the block is 5.0 kilograms, then you can find the coefficient of friction, of static friction. And then it says if the 40 Newton force continues, the box accelerates at this force. So then you'd work backwards from here to get the acceleration. So I'm not going to work that one out. Yeah, 38 we can, let's see, if the coefficient of kinetic friction was 35 kilogram K and 4. So 38 is basically the first part of this one, right? I'm glad we did this one first. It's very simple. You just say friction force has to equal whatever force is pulling it to the right. Might be applied force, tension, whatever it is. When they're equal, it will just get it to move, right?
Also, whenever you try to make set these equations equal, like that's like
It's a minimum.
that's the minimum. That
So like theoretically, if you applied that force exactly, it wouldn't move because it cancels. Yeah, just a billionth of a percent more it would. So that's why that's the minimum. Yeah. Basically, yeah. Okay, so where are the incline problems? Because that's the ones. 53 is right. I bet a lot of people are stuck on this one. Did I not tell you to do 53? Oh no, not 53. 54A and 52, right? Yeah, so let's look at 52 and then we'll do 54A. Because 52 has no friction and then 54 has friction. I think this is really where a lot of you are stuck on forces. And the incline problem is just like, it's physics. Like you see this all over APB, APC, you see it in college physics. It's just a very common situation. So in 52, let's see, our angle is 22 degrees. Let's see. Smooth plane, so there's no friction. Let's see. Does it not give us the mass of the block? Oh, that's fine. We don't need the mass of the block. Right, so the block has a mass m. And it asks, what is the acceleration of the block as it slides down the plane? Right? So a really simple situation here. If you remember what I told you to memorize, the force, so here, what I'm going to do is I'm going to redraw my block as if it's on a flat plane. Right? I know it's not. The force that pulls into the incline, the one that cores, is going to be equal to Fg cosine theta. Right, and the one that makes it slide down the incline, why does it keep doing that? It's going to be equal to Fg sine
Wait, what just
theta.
happened right there?
I don't know.
I think it has to do with the button.
Maybe. I'm not sure.
Wait, because it does that for another.
It only does this when I record it. And I think it's actually, this laptop is so bad that it like gets caught up sometimes and it thinks I'm moving the pen way over there when I'm doing that. So let me redraw this because that's ugly.
It's a nice triangle.
Yeah.
Your lines are right there.
I mean, this is the thing I told you to memorize, and just in free body diagram form. So I'll try to draw it slower. My laptop doesn't freak out. The force that pulls it into the plane is Fg cosine theta. And the force that pulls it down and makes it slide is Fg sine theta. Alright, so if we want to find the acceleration of the block without friction as it slides down the ramp, this force doesn't matter unless there's friction.
It's only sliding.
Right? Yeah, because this is what's going to cause our normal force, right? So this force we don't need to look at for part A. So we could say, finding the acceleration, we know the net force of the block is just going to equal this. mg sine theta. And taking it one step further, ma is equal to mg sine theta. You'll see what happens to the masses.
Where
Net force is equal to ma. F net equals ma.
Oh, yeah.
What happens to the masses? See, we don't have to know the mass. That's why I said, oh, it doesn't matter. So we say A is equal to 9.8 sine of 22 degrees. And that's how you get the answer there. That's essentially like the first step in a block problem, inclined plane problem.
It's not that hard.
If it has friction, we just
That's what we're about to do.
subtract cosine theta.
We're about to do that.
Without friction though.
Okay, so part 54 says repeat question number 52, but now we have a coefficient of friction. This is 22 degrees.
54.
Yeah, this is 54. Right. Now we have a coefficient of friction equal to 0.20. Block of mass m. So looking again at our free body diagram, we're going to have Fg cosine theta. The normal force is also equal to Fg cosine theta. Right. This is going to be Fg sine theta. And the force pulling it up the ramp is going to be our frictional force, which we know is normal times mu. Okay, so now we get a new equation. We say the net force on the block has to equal the sliding force, Fg sine theta, minus our frictional force, Fg cosine theta mu. Alright, same sort of thing's going to happen here. Net force is equal to ma. Mg sine theta minus mg cosine theta mu. All of these m's cancel. And the acceleration is independent of the mass.
Oh my god, you get this.
Right? So A is going to equal 9.8 sine 22 degrees minus 9.8 cosine 22 degrees times 0.2. And that's how you get the acceleration there.
That is 0.
Yeah.
I get
Now
it.
I haven't
These I get.
yeah, well this is just finding the acceleration. Right?
Let's do that.
Well actually this is probably how I should have shown you how to work it out first.
How is
Yeah, see, like, this makes a lot of sense, like,
Well, I think when you can cancel out the masses, it looks easier. But I really wanted us to look at the different forces too. Because the way I showed you to solve for it is find this force, subtract them, right, then solve for A. But you can't, on all inclined plane problems, if it's just the block sliding, like there's not another block hanging off and pulling it or anything like that, it's just sliding, then the mass is always going to cancel out in your net force equation. Makes things easier. I wonder if that's how the book did it.
So if there is mass,
Then you can just put the masses in if you want. But if you set it up this way, it doesn't matter. You don't even need the mass.
So let's say I hang a block off the top end of it.
Yeah.
For the first mass times acceleration, would I just put the mass in for that block there, and then I put the mass in for the middle block? So
Well, what you'd have for your free body diagram, Mac has a good question. You guys probably want to listen to this. Mac's asking, okay, what if we have this inclined plane problem, but we add another block hanging off the edge, and they're attached by a pulley?
don't tell me that's what it says.
I don't know if there's an incline one. I think there might be a multiple choice problem like this. I don't remember.
The friction force plus tension
Yeah.
force.
This is M2. So the way my free body diagram changes is now I'm also going to have pointing this way the tension force. Right? And the tension force is just going to be equal to this. So here we'd say tension has to equal M2 G. Right? So this equation would change because now you're going to have two things you're subtracting.
So what about, could I just put the mass and the mass times acceleration there, and then put mass in the small block and the mass times
Right.
sign?
Yeah, exactly. So you do M1 plus M2 times A, and then you'd have another term here minus M2G.
Why is it M1 plus M2?
Because once again, you have to treat it as a whole system. To find the accelerate, they're going to accelerate at the same acceleration, but they're attached by a string. So you have to say M1 plus M2. Because the forces are going to act on both blocks since they're attached.
But we're talking about the mass, so
Yeah.
if we're subtracting, we're sort of like getting the new mass from subtracting the new. Well, I guess you could get negative mass.
Let's go ahead and do this. I think this is worth working out. We'll do an example problem like this. All right, so same situation, inclined plane. All right, angle of 22 degrees. Don't know the mass, it's just M. Okay, there's another mass, M2. They're attached by a pulley, right? And we're gonna try to find what is the acceleration of the system. All right, so let's look at the two free body diagrams. That's how we're gonna make all our decisions. All right, for the one on the inclined plane, we have FG cosine theta. Right, this is also FG cosine theta. Pulling up the plane, we have FG cosine theta. Let's do mu. Let's say mu is equal to 0.2 again. Y sine.
Why is it FG
Because
cosine?
if you think about, yeah, because like the force is pulling it. Like,
Dude, I'm just looking at this block.
Yeah.
Nothing's changed for the free body diagram of this block in terms of how gravity acts on it. This is going to be, so far this is the exact same free body diagram. The only difference is because of this block hanging off the end, we have one more force going up the ramp. Okay, and we're just going to say this is equal to the tension force for now. Right? Looking at the other block, it has two forces acting on it, Fg, which is going to be equal to M2A, or sorry, M2G, and the tension force.
Wait, what do you mean for now? For now.
Huh?
Isn't it always equal to tension?
Over here, well, I'm just saying Ft for now. We're going to figure out what it is in terms of M's and A's and stuff. Right? So the tension force is resulting from this force right here. That's the only place that's going to supply that tension force. Is there another way to state this? I'm trying to think. Like if we wrote the net force equation over here, the net force on this block would be Fg minus Ft, right? Well, this is not 0. Okay. This would be M2A equals Fg minus Ft. So the tension force would equal Fg minus M2A.
But then what do we need to know the mass?
You'd have, yeah, I'm solving in terms of variables right now. Okay, so what this means is either the force of gravity is going to be greater than this tension force pulling back resulting from this block. You see, that's one situation, right? If this is bigger than this, then it's going to accelerate this way. But this block is going to slow it down some because it's going to pull back on it, force of tension. The other way is if this block is bigger than this one mass-wise. Well, actually, it doesn't have to. Let me show you. It doesn't have to do with the mass completely. All right, so what we can say now is this force of tension is equal to Fg minus M2A. right? Wait, what do I'm not going to use the FG. M2G. There we go. Minus M2A. Now the accelerations of both blocks have to be the same. So when we go to write the final net force equation, it'll look like this for this block, for example. Try to remember all of this. So if we're just doing it for the first block, it would be M1A has to equal, let's do right as positive. So M1G cosine theta mu plus the tension force, which was, so M2G minus M2A. Acceleration here being the same as this one. Looking at the picture, see this plus this. I'm saying this is the positive direction here. So this plus this, and then I'm going to subtract this. Minus M1G sine theta. So you'll see here that your masses don't cancel out in this problem. You have to know the masses of the blocks here, because that's how your equilibrium gets set up, right? For the acceleration of the system, yeah. So I think, how is the best way to visualize this? I'm going to go ahead and divide through by M1. So this M1 cancels out, this one M1 cancels out. So we say that acceleration of block 1, well, both blocks, is equal to G cosine theta mu plus M2G minus M2A over M1 minus G sine theta mu. All of these G's are constants, they're never going to change. So really the acceleration depends on first the coefficient of friction, the mass of block 2 minus the mass of block 2 times the acceleration divided by M1. This is the ratio that we needed to look at. So if M2 is greater, M2 times gravity is greater than the mass of block 1 times the cosine theta of mu, like, where? Visually though, let's look at it. I mean, that would be the final equation. If this force here is greater than this force, or actually these two forces added together, and keep forgetting about that, there's friction. You know what I just realized is that your frictional force is going to change depending on which way it accelerates in. Yeah.
Yeah.
But this is a little more complicated. So,
So it's all wrong?
no, it's right. I assumed that this mass, this force is greater than this one. So you'd have to set it up and figure that out before you dealt with the frictional forces.
Okay.
So if this is bigger than the tension force,
You're essentially pulling against gravity and that's
Right.
pulling the distance.
Yeah. So if this is greater than the tension force, it's going to slide this way. Frictional force will oppose its motion. Right. Okay. But if the tension force is bigger than this force, then it's going to slide this way, and the frictional forces will point the other way. So yes, whoops.
Oh,
I kicked it too. Okay. So, confusing problem, but I think seeing this will help you on the test. I don't think there's one with this, especially one with friction. There might be a setup like this, but it would be without friction, which is really easy. Because then you don't have to worry about which direction it's moving in. It's relatively simple.
I see what you did. It wouldn't be going against gravity, so that would make it need more force.
Sorry?
Well, even without friction.
I can. I honestly, I don't think it's, well,
So
That's the more problem.
how is the force going down the slope the same?